Welcome back to another lecture from organic chemistry. In this lecture, I'm going to go through Fisher projection. I will try to show you how to run Fisher projection and also assign the configuration for each stereocenter. Okay, so from now, we're going to say the horizontal lines are pointing to us, while the vertical line are back of the molecule. So as you see here, the vertical will be H and OH, and H and OH are pointing to us, while the ethyl and methyl, they will be back of the molecule. Okay, let's practice some example about them. This is the molecule that we have. So I'm going to say I have a carbon, and that carbon is attached to methyl. Here you go, CH3, and then attached to ethyl, and that's going to be ethyl. We have two carbons there. Okay, and I have I have hydrogen and OH. Hydrogen, I'm going to show it by with, and same thing for OH, and that means those two are facing to us, while the methyl and ethyl, they will be back of the molecule. Okay, they are supposed to be back of the molecule. So I can just simply erase those and show them by dashed line just to say that they are back of the molecule. But for easiness, and most of the time you will see people are just simply, they are drawing it like a cross, and they said, okay, we have methyl down here, and this is ethyl, and now we have hydrogen and OH there. I'm going to show that hydrogen and OH are pointing to us, so I'm going to give them with. Now we'll fill in those to show that those two are facing to us. And remember, if hydrogen is facing to you, and whenever you want to try to figure the configuration, you have to flip it. Okay, so let's assign the configuration. This is going to be 1, then ethyl, it will be number 2, methyl number 3. How about hydrogen is going to be the 4th one? If I follow the numbers from 1, 2, 3, okay, it's telling me this is going to be clockwise. It will be R. But I'm going to ask myself, where's hydrogen? Pointing to us. Okay, pointing to us. Because it's pointing to us, you have to flip it and you write it as S. Okay, and that's going to be the right configuration. Another one, we have structure that it has 2 OHs, and on the top we have aldehyde functional group, and this one is going to be alcohol. Okay, so there is no plane of symmetry in this case. I can just simply cut the molecule to half, and not only OH with H will not be mirrored. Those two groups are not going to get mirrored. So I'm not dealing with like a mesostructure. Okay, I have 2 stereocenters. One is here, and that's going to be the second stereocenter. Let's highlight them. Okay, as you see, I showed the H and OH are pointing to us, and let's assign the configuration for each one. Okay, so we're going to start from if this one, okay, let's say this is carbon number 1, 2, 3, and that's going to be 4. Okay, if you go, for example, that way, and so then I'm going to say this one will get the first priority, and then that one. Why that carbon? Because that carbon is attached to oxygen through a double bond. So you can assume that carbon is attached to 2 oxygen and 1 hydrogen. But what do we have attached to this carbon? We have hydrogen. Okay, yes, we have hydrogen also there. We have 1 oxygen, and then the third one will be carbon. Okay, well, the top one, it has 2 oxygen, 1 hydrogen. The bottom one, it has 1 oxygen, 1 carbon, and 1 hydrogen. So this is going to be number 3. And if you follow the order, this is supposed to be counterclockwise, but because hydrogen is pointing to you, you say this is supposed to be S, but we're going to flip it and it will be R. Okay, let's practice this one for this next carbon. For this carbon, so we're going to say this one is going to be the first priority, and next we're going to have that carbon. Why that carbon? Why not the bottom one? That carbon is attached to oxygen, hydrogen, and carbon. So oxygen, carbon, hydrogen. You can say OCH. Well, this carbon, the bottom one, is attached to oxygen, hydrogen, and hydrogen. Look to this. Okay. The second atom is carbon, while the bottom one is hydrogen. So I'm going to say the top one will get the second priority, and this one will get the third priority, and hydrogen will be number 4. Okay, so if we follow the numbers, this one is a clockwise, so it's supposed to be R, but because hydrogen, number 4, hydrogen is facing to us, it will be S. So the configuration, we got R here, and this one we got S, and I'm going to highlight them. Those are the right configurations. Okay, so we got R and S. Let's write them. We got R and S. Okay, double check. We got R and S. Now I want to know what's the relationship between these two. So what did I do? Track OH. OH is on the right side here. OH went to the left side. Okay. How about this OH? This OH used to be on the left side. Now we moved it to the right side. So we flipped position of, like the OHs. We had R and S. If you flip position of which substituent? We flip position of H and OH. Okay. We flip position of those two. If you flip position of 2 of the substituent, Okay, if you flip position of the substituent, the configuration it will be inverted. So if this one is R, that's supposed to be S. This one's supposed to be S. Let's double check it. So I'm saying this one's supposed to be S. Okay, this is going to be number 1, that's number 2, and this one is going to be number 3. So the five following numbers is supposed to be R because it's clockwise, but hydrogen is facing to us, so it will be S. Okay, and next one, I get number 1 here. Okay, this is going to be number 2, and that one will be number 3. So in this case, it's supposed to be counterclockwise, but because we have hydrogen facing to us, it will be R. So I got S and R. Okay, I got S here and R. Remember, we started from R. Okay, turn to S, and the second one is S, turn to R. Okay, what's the relationship between number 1 and number 2? Okay, I see the same chemical formulas, but the centers, the configuration got inverted. So you had R and S, now they turn to S and R, S and R. Okay, so I got S and R, well, they used to be R and S. Okay, because I inverted the configuration, I'm going to say I'm dealing with a non-two mers. Those two are enantiomers. Okay, how about here? Okay, we have R, and this one is S. Okay, what did I do? I flipped position of them. Okay, so we had OH here, OH there. Okay, we flipped position of one of the OH, but the second one we kept it as it is. We didn't change the second one. Okay, so I'm going to say the second configuration, second carbon is going to have S configuration, but the top one, because I flipped the position as I showed it on the top, that's going to be S. Okay, S. So we had R and S. We turned it to S and S. Okay, one of them did not change. Okay, one of them did not change. So I can write it underneath of it. So first carbon is S, and the second carbon still is S. Okay, this one got inverted, but that one, the second one, remained the same. So I'm going to say, what's the relationship between those two? Okay. Those two between, again, number 1, let's call this one number 3. Number 1 and number 3, they will be diastereomers. Those two are diastereomers. Diastereomers, one of the configuration, one of the stereocenters, one of the stereocenters remained the same, did not change. And because it did not change in this case, I'm going to call it diastereomer. Okay. In these two, if you look to them, you might say, oh, I have a mirror. No, you don't have a mirror because this is R1 and R2. They didn't say anything about them, and but they live differently. So I'm going to say there is no mirror. Okay. They changed position of the bromines because they moved them. Okay. They used to be on the right side. They moved them to the left side. Those two are going to be enantiomers. Okay. Now, these two, okay, on the right side, okay, they kept one of them on the right. They flipped position of that one. Okay, the second. So these two are going to be diastereomer. Okay, and then proof for it. And okay, I can't assign the configuration for each one because I don't know R1, and so it's going to be hard to assign it. And because we don't know R1 or R2, but the only thing I can say, because they kept one of them. So let me highlight this. They kept this center the same, so that's stereocenter is going to be the same, but the second one, okay, the second one got flipped. They flipped this one because they flipped it. So I'm going to say the configuration here got flipped, while there they are the same configuration. So those two are going to be diastereomers. We talked about this. We said we have a gauge conformation here. and you look to the methyls, the degree between them is 60, but one of the methyl is on the right side. And this time we get the angle, dihedral angle between them again is 60. I'm going to call it gouge, but the difference between them, the methyl now is on my left hand. Okay, left hand. And when I say left hand, I'm treating this one as a reference. Okay, and methyl used to be on the right side. Okay, now is on the left side. Okay, what's the relationship between these two? So we said if you get two different 3D geometries by rotation through around single bond, you will get stereo isomers, and those two isomers we call them conformational isomers. Okay. Are they mirror image of it? Do you have a stereo? Do you have like an inversion center here? There is no mirror. Okay, there is no mirror here. There is no inversion. Okay, they look. Okay, they are a mirror image of each other. Okay, if you put a mirror somewhere here, okay, they looks like mirror image of each other. Okay, so should I call them an enantiomer? Until now, yes. We can call them an enantiomer until now, but because we have a single carbon-carbon bond, and rotation around single carbon-carbon is feasible. It's really easy. You cannot separate those two conformational isomers from each other, because you cannot separate them. You will always have 50-50 from both of them, and the solution will be not active. So you are not gonna get any rotation. Rotation is gonna be 0, and we say non-active, or optically not active. You are not gonna see any chirality, okay? Because rotation around single carbon-carbon bond is feasible. Okay. How about this tropisomers? Tropisomers are molecules that, because of the geometry, rotation around a single carbon-carbon bond, it will not be feasible. Okay. In this case, we have a single bond. I'm going to highlight it. That's a single bond. So I'm supposed to get, freedom of like rotation around that single bond. Okay. And these two, they can cross each other. And it depends where they are standing. I get different isomers. I might get R or S, for example. But in this case, because we have a bulky group, those two bulky group very soon are going to see each other. And when they get too close to each other, okay, they cannot cross or they cannot pass each other. They will be fixed. Why? Because they are too close, and repulsion between them will repel them. And so the system will be locked. Okay, system will be locked or stuck in a specific position. In that case, we say we got isomer because of the steric effect, and that's the reason we call them tropisomers. Tropisomers are isomers that there is no stereocenter here. Okay, we don't have a stereocenter, but because of steric effect, they are stuck in a specific orientation or position, and that's the reason we call them chiral compounds. And another way to lock the system is whenever you have a bunch of double bonds back to back, and in this case, we're going to call the compound allenes. Allenes, you have a carbon that is involved in two double bonds. Okay, two double bonds. So rotation, this direction around that carbon is not feasible. And same thing here, we can't have any rotation. So that carbon is locked. Okay, it's locked. Now, if you try to draw a mirror image of it, you will see that in this distance you're going to have hydrogen, and in this distance you're going to have methyl. Okay, are they mirror image of each other? Yes. They are mirror image of each other. Do I have a stereo center? No. Okay, so no stereo center. Okay. So is it possible to call it chiral without having without having a stereo center? Yes. This molecule, like a previous one, again, we don't have a stereo center, but because of the two double bond, the system it will be stuck or locked in a specific position. Even we don't have a stereo center, still the molecule will be chiral. Why chiral? Because I can see different substituent there. On each carbon, I see different substituent. So that molecule, it will be chiral. Okay, so these two molecules, they don't have stereo centers, but still we have chirality because of lack, okay? Because the system got locked in a specific position. subject that I want to talk about it. Enantiomers are identical mirror image of each other, but not superimposable. They do have exactly the same boiling temperature or physical properties. So how do you want to separate them? Okay, how do you want to separate them? Okay, we know this. We know if we turn them to diastereomers, okay, if we turn them to diastereomers, as you see, diastereomers, they have different physical properties. So if you turn an enantiomer to diastereomer, you can separate it. For example, one enantiomer, two enantiomers are both enantiomers are soluble, but if you turn them to diastereomers, maybe one of the diastereomer is not soluble and it will crash, it will turn to solid. So this is the technique that we use to separate enantiomers from each other. In this case, I have 1, 2, 3. This is gonna be S configuration, and here 1, 2, 3, because hydrogen is facing to us. Okay, this is gonna be R configuration. So S and R, those two are enantiomers. Next, we have 1, 2, 3. This is gonna be R S configuration. S configuration. So I have enantiomers, two enantiomers, and I'm treating them with a chemical compound that it has S configuration. What do I get? I get S, and this one is S. And here we got R, but that one still is S. Okay, look at this. One of the stereocenters got flipped, but the second remained the same. Now, what's the relationship between number 1 and number 2? I'm going to say number 1 and number 2 are diastereomers. And because they are diastereomers, I can separate them because they will have different physical properties.